Hi, welcome back to es346 Basic Thermodynamics. This is module 5.5, Unsteady Open System. The section in the textbook is section 5.5. Here are the two learning objectives for this module. At the end, you'll be able to determine the first law energy balance for an unsteady open system, and you'll be able to calculate property changes for an open unsteady system. First, I want to talk about control volumes that we use for open systems. So on the left here, I show a diagram of a control volume that's a rigid tank, and it has a supply line so that material is able to enter the system. So it's clearly an open system, material is crossing the boundary. It's easy for me to define my control volume. It's simply the boundary of this rigid tank, which doesn't change. And that's a common control volume I might use. Now, another option, though, would be illustrated with this piston cylinder, where now I've got a volume that can change. And so as I add material in the bottom of the piston cylinder, this piston, for example, may go up and the volume would increase. So here I'm defining a control volume, but a volume that changes. And that's okay, as long as I know where the control volume is and what material is crossing my boundary. So for example, if I keep the top surface of my control volume right at the bottom of that piston, such that no material is able to cross that boundary, I only need to account for the material crossing down here, and that way I will know the amount of material and thus the amount of energy that goes in. So my control volumes could be fixed, or my control volumes can be variable. All right, let's go ahead and derive the first law energy balance, just the general form. And so I'm going to draw up a piston cylinder, and it has an inlet, and it also has an outlet, and it might be moving up or down. So kind of a most general open system. Write our energy balance. So the change in energy of our system, the energy that goes in minus the energy that goes out. And the change in energy of my system is going to be m2u2 minus m1u1. So this is the internal energy at the beginning is m1u1. That's the internal energy at the end. And I'm using u here because this is accounting for material that stays within my control volume. Now, if I look at the energy that enters my system, I'm going to have the mass flow rate that goes in times h, the enthalpy, its kinetic energy term, v squared, plus its potential energy, gz. And I also could have heat going in, Qn, and work that goes in. And let's go ahead and subtract material or energy that's leaving the system. So now I'm going to have mass flow rate that goes out, its enthalpy, its kinetic energy term, and its potential energy term. And then also subtract any Q that leaves and any work that leaves. So there I have my most general energy balance for an open, unsteady system. Now I can also do a mass balance. And since we have mass changing in open systems, that's an important equation to go ahead and use. It's not trivial. And so again, I know that the change in mass, which is m2 minus m1, is going to be that which goes in minus what goes out, m in minus m out. So the mass balance looks a lot like the energy balance. We see our m2, m1 term and our m in and m out terms. We're just not multiplying each one by a related energy term, and there's no q's and w's in it. So I have two tools I'm using, an energy balance and a mass balance in these open, unsteady systems. All right, here's an example. And I'm asked to determine the direction and the amount of heat for this system in which the temperature remains constant. So let me go ahead and explain what's going on here. I have water, and it's in a rigid tank. It's initially, or it's actually, the volume is always held constant at 0.3 cubic meters. The temperature is 200 degrees Celsius, and that has to remain constant. And it starts off full of saturated liquid. Now, a valve is opened on the bottom, and half of the original mass leaves the system. Now, another thing that happens is Q, there's some amount of heat transfer. It either enters or leaves such that the temperature remains constant. So the temperature is going to remain constant, 200 degrees Celsius. And I need to determine the direction and then also determine the magnitude. That's what the problem is looking for. Let's go ahead and write down our energy balance. Change in energy is energy that goes in minus energy that goes out. And this will be m2u2 minus m1u1. And let's look at what energy goes into the system. And what I see is that, well, I don't know if Q goes in or out. So let's just assume that Q goes in. So we'll say Q in is the energy that goes in. And then the energy that's leaving, the only one I'm told is this mass that leaves, so that's going to be m out times h out. And it's its enthalpy because this material crosses the boundary. The stuff over here I multiply by internal energy because that remains within my control volume, within the boundary of the system. So let's go ahead and look at what intensive variables we know, because we're going to have a lot of properties that we need to determine. And I'm told in the problem that the temperature starts off at 200 degrees Celsius, and it remains constant, so that's also equal to T2. So therefore I have one intensive variable so far, at both the initial and final state. I'm also told that it starts as a saturated liquid, so that means that x1 is equal to 0. So I have a pair of intensive variables at the initial state, so that'll permit me to find out what is U1, that internal energy. But I don't have another intensive variable at the final state in order to find U2. So I'm going to need to use another tool, and that's why I'll use the mass balance. It says that M2 minus M1 is equal to, well, no mass goes in, 0 minus the mass that goes out. But I don't really know what those mass terms are, and in fact I'm going to need them in the energy balance. But there's another piece of information here. I see I have the total volume at 0.3 cubic meters. And with this pair of intensive variables, I can find little v1. So that tells me I can go ahead and find out, calculate what m1 is. m1 is going to be equal to the extensive volume over the intensive volume, little v1. And this I can find. I'm going to find this off the table. It's v sub f. So I can go ahead and calculate that right away. At 0.3 cubic meters, and the value of v sub f at 200 degrees Celsius is 0.00157. So that gives me what my initial mass is at 259.3 kilograms. And now there's some more stuff I can do here, because I know that 1/2 of the mass leaves. So m out is 1/2 of m1. And so then m out is going to be 129.65. And in fact, m out is also then going to end up being m2. 1/2 of the mass leaves, 1/2 is left in. So now I know what m1, m2, and m out is, which is good because I can also put those back up into my energy balance. But I haven't done anything for finding intensive variables. But now I know m2. And there's an extensive variable, and the volume remains constant. So this up here, this big V1, is also big V2. So that's going to go ahead and let me find out what little V2 is. So little V2 is the volume over M2. That extensive volume doesn't change. It's a rigid tank at 0.3. So I have 0.3 over M2, which is 129.65. And that gives me 0.00231 units of meters cubed per kilogram. So now I have a V2. So I have another pair of intensive variables that's going to go ahead and let me find U2. So I'm making some good progress here. I have all my mass values. I can find both U1 and U2. And the last thing it's going to be is this enthalpy. So we can go ahead and start plugging some values in here. So let me move to a new page. I rewrote the energy balance that I have. And here's the pairs of terms I have. I just found what V2 was. And so let's go ahead and start calculating what my internal energies are. And I'll just move across. So I want to find U2. And the pair of variables I'm using are T2 and V2. And so if I look at this value of V2, I'm going to realize that V2 is between VF and VG at 200 degrees Celsius, which means that I have a mixture. So in order to find that, I can go ahead and calculate my quality, V2 minus VF over VG minus VF. That's equal to X2. And then that's what I'm going to use to find my internal energy. So I can write that as U2 minus UF over UG minus UF. Those values are also at 200 degrees Celsius. And so using that value of V2 that I have, I'm going to use that to go ahead and find out what U2 is. And so U2 from that equation is 866.5 kilojoules per kilogram. So there's my value of U2. So I'm moving across. I already calculated my mass. I need to find what U1 is, given X1 and T1. Well, U1 is UF at 200 degrees Celsius. So that's going to be 8. 50.5 kilojoules per kilogram. So I'm doing pretty good. The only thing left, I'm using that equation to find Q, is to find H out. So looking here, I've got this valve that's on the bottom, so probably what's happening is all the liquid's moving out. So H out that's leaving is going to be that saturated liquid that's moving on the bottom. That's HF, and that is 852.3 kilojoules per kilogram. Just find the table. So all those are 200 degrees Celsius. So now I can plug all that in to solve for Q. And Q in, I do all the arithmetic, is a positive value of 2307 kilojoules. So first of all, I assumed the direction correctly because I calculated a positive value. So Q goes in, and this much heat goes in order to keep the temperature constant in the tank after I remove 1/2 of the mass. All right, I want to talk a little bit more about open systems now, though, but some of the implications with ideal gases. And there's a couple things here that are a little bit unintuitive. And so let's look at this system here, where I have a rigid tank. It's got air. I've got 1 kilogram at 25 degrees Celsius. And what I'm going to do is I'm going to put in this little chunk of material that's also air, 1 kilogram also at 25 degrees Celsius. I'm going to put it into that tank. And so I'm adding something at 25 to something that's at 25. And it seems like, gosh, it should probably stay at 25. But it turns out that that's not actually true. If this is a rigid tank, it takes some work to go ahead and put it into that tank. And those temperatures don't remain constant. So let's go ahead and find out what that temperature would be using the energy balance. So the change in energy is going to be the energy that goes in minus energy that goes out. And in my system, I'm just putting energy in. So I've got that. Change in energy is just the energy that goes in. So that's going to be M2U2 minus M1U1. So my change in energy is the energy that goes in, which is M in H going in. And now I have an ideal gas, and so U is CD times temperature, and H is CP times temperature. So I can go ahead and put those terms in there as well. And I know what my mass are. I've got 1 kilogram initially, add 1. So M2 is going to be 2 kilograms, and U is CD times T2, which is what I'm attempting to calculate, minus M1. I start off with 1 kilogram of mass. CV times the initial temperature is 298. And that right there is equal to the mass that goes in, which is just 1, times the heat capacity, C sub P, times that temperature coming in, which is 298. So I have one equation now. CV for air is about 0.718. CP is about 1.005. So I can go ahead and put that in to calculate what T2 is. And if you do that arithmetic, you find out that T2 is about 357.6. This is in Kelvin. I converted my degrees Celsius to Kelvin. So this is much higher than 298. It's about 75 degrees warmer. It's sort of counterintuitive. If you add something at 25 to something at 25, I get something that's a lot warmer. And it's because I didn't just stick them together. I actually pushed this material in, and that work that I did to put it in, that energy is now contained inside here in the form of thermal energy. Okay, so let's do another example where we're now using ideal gases. And this problem is going to be a little bit more involved. But what we want to know is we want to find out the temperature is in this balloon. So I have a balloon that I'm showing here, and I've got material coming in at 100 degrees Celsius. And the pressure in the balloon changes with the volume. So imagine blowing up a balloon where the pressure inside changes as a function of volume. And I'm given this equation here. The pressure is 100 times the volume plus the atmospheric pressure. And so this balloon will have initially start off at 0. So V1 will be 0. And then we want to know what the final temperature is. And so I didn't write it on here. We'll have the final volume equal to 4 cubic meters. And let's find out what that final temperature is in the balloon. So let's start off with our energy balance. Change in energy is energy in minus energy out. And so change in energy is going to be M2U2 minus M1U1. And then if I look at what goes in, I've got this air that I'm putting into the system. So it's going to be M in times H in. And since this is a balloon and it's expanding, I'm going to have to go ahead and subtract the boundary work. All right. If we assume that the balloon is initially unfilled, there would be no M1 term, so we can go ahead and cancel that term out. And that just means the amount of material I put in is M2. So M2 is equal to M, and I'll just go ahead and start calling that M, the amount of mass that I have. So, now, here's this boundary work term that I need to calculate, and I have a pressure that's not constant. So this will be a little complicated, but let's go ahead and do it. So we know boundary work is the integral of PdV. And so what we're going to integrate, so I'm going to put in this expression for pressure, 100 times V plus PATM. All right. And I'm going to integrate that from 0 to 4 cubic meters. That's my final volume. So if I go ahead and do that integral there, I'm going to end up with 1/2 of 100. This will be 50 V squared plus PATM times V. And I'm evaluating that from 0 to 4. Now PATM, I'll put that, it's about 100 kilopascals, and so now I can calculate what this total work is. I have 4 squared is 16 times 50. So that's going to be 800 plus 100 times 4 plus 400, so 1200 kilojoules. That's the boundary work term. So that's the WD term that I'm going to go ahead and put in there. Now, also, one more thing I can do is determine what this mass 2 is, which is actually the only mass that I have in the system from the ideal gas law. So M2 is equal to P2 V2 over R P2. And so I can calculate what the final pressure is. So again, the final pressure, P2, is 100 times 4 plus 100, or 500. So that's going to go ahead and give me 500 there. And then I need to multiply that by the volume of 4 over R times P2. So that's going to end up being equal to 2,000 over R P2 is equal to M2. All right, so let's go ahead and finish up this problem. I'm going to rewrite my energy balance. Go ahead. M2U2 is equal to M in H in minus the boundary work. And so we can go ahead and put in our terms. So this is an ideal gas. So it's going to be M times CV T2, so I'm trying to find. This is M. Remember, all my masses were constant. It will be CP times P in, and that's going to be minus my boundary work that I calculated before at 1200. And so now we can go ahead and put in that expression that we had for the mass, because we just found mass. So mass, remember, was P2 V2 over R T2. CV T2 is equal to P2 V2 over R P2. CP Tn is 100, or 373. And then the boundary work we calculated before, boundary work was at 1200. My T2s there actually cancel. So now if I go ahead and put in all my numbers, I can calculate what T2 is. Some arithmetic in there, but if you calculate T2, you'll find out that's 421 Kelvin, or about 148 degrees Celsius. So again, it's sort of a counterintuitive result. I'm putting air in that's 100 degrees Celsius, and it seems like it's heating up. Well, the reason it's heating up is because I'm requiring work to put it in, and even though it's doing some boundary work, it's not doing enough to counter effect, and it still ends up warming up to 148 degrees Celsius.